In the last lecture, we were able to, purely by examination of the structure of the angular momentum operators, derive the quantization properties of angular momentum in quantum mechanics. We were able to examine the commutators, manipulate the operators, and essentially derive the eigenvalues associated with the operators L squared and L sub z. That's nice, and it's very useful. The eigenstates associated with Hermitian operators in the Hilbert space have nice properties, but we don't actually know what those eigenstates look like. In order to get something easier to visualize, let's consider what the eigenfunctions are, trying to express the angular momentum operators as partial differential equations that we can solve with the techniques that we've been applying earlier in this chapter. The angular momentum operators that we were working with in the last lecture are expressed in Cartesian coordinates. This was very nice because the Cartesian form has this nice symmetry to it, and we could calculate commutators easily. Just by manipulating these, we were able to derive expressions like the eigenfunctions of L squared had this sort of form. H bar squared L plus 1 was our eigenvalue. Likewise, for L sub z, we ended up with eigenvalues of the form m times some constant h bar. The L's that we got had to be half integers, either 0 or 1/2 or 1 or 3/2, etc. And the constants m that we got here had to be between minus L and L, going up in steps of 1. So our eigenvalue structure here, as I mentioned, doesn't tell us anything about the actual form of f. When we were working with the one-dimensional quantum harmonic oscillator, we were able to derive, for instance, the ground state by knowing that the lowering operator acting on the ground state gave us 0. That was a differential equation that we could work with since we knew differential forms for the lowering operator. We can do the same thing with the angular momentum operators, but in this case, it's more worthwhile to think more generally. So suppose we just have some general psi of r, theta, and phi. This is our wave function expressed in general polar coordinates, and it would be nice to know how our angular momentum operators act on this general wave function. If we can express our angular momentum operators in spherical coordinates, we can write down this sort of eigenvalue equation. It will then be a partial differential equation that we can solve, in general, for any value of L or M. Unfortunately, in this lecture, we run into some thorny notational issues. I like to use hats to designate operators. Griffiths, your textbook author, likes to leave the hats off when it's not ambiguous. This is one of those cases where it is ambiguous, and I would like to use the hats, but unfortunately, hats are also significant in other ways. In particular, hats in this section of the textbook mean unit vectors. So I'm going to try and follow Griffith's notation, and I'm going to try and point out where things are operators and where things are unit vectors. But in this case, in this lecture, if I write something like Lx, I mean the operator. And if I write something like r hat, I mean the unit vector. Like I said, I'll try and be clear about what I mean in each case. At any rate, our goal here is to come up with spherical coordinates expressions for the operators that we were working with when we were considering angular momentum operator algebra, L squared and L sub z. So first of all, let's consider just L in spherical coordinates. There's going to be a lot of math in this lecture, and I'm going to go through it only conceptually. The level of grunge in this sort of coordinate transformation is above and beyond what I would expect you to be able to do for an exam. So, most important, I need you to understand the overall structure, the sorts of manipulations that are being done. Change of variables in the context of partial differential equations is tricky, so let's try and just understand overall how it works. First of all, what we're working with is angular momentum, L, which is given by r cross p. Now, I've left both vector hats and operator hats off of these, but this is the angular momentum operator, this is the position operator in spherical coordinates, and this is the momentum operator in spherical coordinates. The momentum operator in spherical coordinates is rather straightforward to write down. We can write it as minus I h bar times this gradient operator, del, which you know as, I'll write it in Cartesian coordinates, x hat times the partial derivative of x plus y hat times the partial derivative with respect to y plus z hat times the partial derivative with respect to z. You can apply this to an arbitrary function of x, y, and z, a scalar function, and it will give you a vector. So this is a vector, as is the momentum, So this is a sort of momentum vector operator. This gradient can be expressed in spherical coordinates as well. And expressed in spherical coordinates, it has this partial derivative with respect to r, partial derivative with respect to theta, and with respect to phi. The partial derivatives with respect to theta and phi have to be rescaled, since, for instance, if you consider it in Cartesian coordinates, this is essentially a spatial rate of change. It's a vector that points in the direction that the function changes most quickly with respect to physical space. And a change with respect to theta is not a change with respect to physical space. R d theta is a motion in space, whereas r sine theta d phi is a motion in space. So these are our motions in space, and the rescaling necessary is taken care of by this 1 over r and this 1 over sine theta. This gradient gives us the momentum, which we can cross with the radius operator, the position operator in spherical coordinates, which is quite simply r hat. So this hat now designates a unit vector, and this designates a coordinate. And as usual, our position operator is multiplication by the coordinate in question of, well, the multiplication of this with whatever the operator is acting on, some function in this case. So our angular momentum then is going to be a cross product of something like, I don't know why I erased it, r hat. So I'm going to be taking the cross product of r hat, that's the vector part of my position operator, with this part of my momentum operator. I can pull my minus I h bar out, and this is what you end up with, simply taking cross products r cross theta, and r cross phi. Where here I had a 1 over r in my gradient, but it's been cancelled out by the r coordinate multiplication in my position operator. Likewise for phi. There was a 1 over r here as well. This can be simplified slightly. You know that r cross r is going to be 0. The cross product of any vector with itself is going to be 0, since the cross product depends on the angle between the vectors. They have to be pointing in different directions. R cross theta is going to give me phi hat, a unit vector pointing in the phi hat direction. And r cross phi is going to give me minus theta hat, a unit vector pointing in the minus theta direction. You can, therefore, you're only going to end up with two terms, and that will be our angular momentum operator. Since, however, what we were actually doing when we were working with L squared and Lz, we needed expressions, for instance, for things like L plus or minus. This L plus or minus was expressed in terms of Lx and Ly, so what we actually need to do is take the overall angular momentum operator in spherical coordinates and use it to find angular momentum operators in Cartesian coordinates expressed in spherical coordinates. Now this is a very strange way of saying things, but essentially what I want is the angular momentum about the x-axis, the x component of the angular momentum, but expressed still in spherical coordinates. The way to do that, and the way Griffiths uses at least, is to take this expression for the angular momentum operator, which has phi hat and theta hat in it, and express the phi hat and the theta hat in Cartesian coordinates. Those Cartesian coordinates values of theta hat and phi hat will depend on theta and phi, so we end up with this weird hybrid Cartesian spherical coordinate system. But doing so allows you to identify the x component of the angular momentum, y component, and z component. If you actually do that, substitute in phi hat in Cartesian coordinates, for instance. Phi hat in Cartesian coordinates, this weird Cartesian spherical coordinate system, is minus sine phi I hat plus cosine of theta j hat, where I hat and j hat now are Cartesian coordinate unit vectors. This would normally be written as x hat in a normal physics class, but of course we know x hat as the x component position operator, and we can't reuse that notation. You can see why I'm sort of glossing over the details of this. Actually doing it all out would require a fair number of slides and a good deal of your time. At any rate, substituting in this expression, for instance, for phi hat, and a similar expression for theta hat, you can identify the I hat component of L, the x component of the angular momentum. And when you do that, this is what you're left with. So the x component of the angular momentum has derivatives with respect to both theta and phi. Likewise for L sub y, the y component of the angular momentum, L sub z, however, only has derivatives with respect to phi, and this should make a fair amount of sense since z is special in spherical coordinates. Phi is the angle that rotates around the z-axis. So that's all well and good. We're starting to work our way towards expressions of the operators that we're actually interested in, L squared and L sub z. We have one for L sub z, but what about L squared? L squared, it turns out, is easy to express if you think about it in terms of the L plus or minus operators. This was the trick that we used back when we were doing operator algebra. L plus or minus, of course, is expressed in terms of Lx and Ly. But we have Lx and Ly now, so we're ready to go. L plus or minus being expressed in terms of Lx and Ly. Going back to your notes from the lecture on the algebraic structure of the angular momentum operators, we can express L squared rather simply in terms of L plus and L minus. L plus and L minus being expressed in terms of Lx and Ly, we can make combinations of Lx and Ly. Multiplying those out is simply an exercise in calculus, multivariable calculus, taking partial derivatives, applying chain rules, etc. When you do all of that, evaluating this expression that we got from the algebraic structure of L squared in terms of L plus, L minus, and Lz squared and Lz, you can go and look that up in your notes, you end up with an expression for L squared. This should start looking reasonably familiar. What I really want to do here is write this into an eigenvalue problem by adding some arbitrary function f. This whole operator, acting on some function f, is going to be equal to, we know what the answer is from our consideration of operator algebra. It's going to be h bar squared L plus 1 times f. It's going to give us our original function back. So this right here, this is our partial differential equation that we can solve for f, where f now is a function of r, theta, and phi, and is going to essentially give us our wave function. We only have angular components here, so there isn't going to be any radial part. That should make a good amount of sense. Radial motion doesn't contribute any angular momentum. We can do something very similar for L sub z. L sub z acting on some arbitrary function, and L sub z we already had an expression for. It was minus I h bar partial derivative with respect to phi of f. We know what that's going to give us already as well, because we know the eigenvalue structure of L sub z as well. It's going to give you m times h bar f. Both of these are going to be then partial differential equations that we can solve. This tells us something about the eigenstates of L sub z. This tells you something about the eigenstates of L squared. And if you look at these equations, they should be familiar. These are the angular equations that we had earlier. These essentially gave us the YLM of theta and phi as their solution. So what we've shown here is that the eigenfunctions associated with the L squared and L sub z operators are exactly the spherical harmonics. The spherical harmonics were what we got from a spherically symmetric potential expressing the time-independent Schrödinger equation in spherical coordinates. And this should make a certain amount of sense, since what we're talking about now is angular momentum, and L squared, for instance, angular momentum squared, has to do with the rotational kinetic energy. So it ought to play some role in the time-independent Schrödinger equation, which tells us the energy of the stationary states. So if we have an eigenvalue of L squared, simultaneous eigenstates of L squared and Lz are exactly the spherical harmonics. There is a slight difference here, and it comes down to the value of L. Essentially, we have two classes of solutions here. We have half-integer L and integer L. Our consideration of spherical harmonics gave us only integer L, whereas, our consideration of wave functions, the solutions to these partial differential equations, give us spherical harmonics, which are only meaningful for integer L, integer L. Half-integer L doesn't really make any sense in the context of spherical harmonics, which means if what we're talking about is angular momentum of something like a physical particle, orbital angular momentum, rotational kinetic energy, essentially, we can't have half-integer L. But we do have these half-integer L solutions. If I'm talking about wave functions, I have to have YLMs for my solution. That means I have to have L being 0, 1, 2, etc. and M being, minus L up to L. If what I'm just talking about, though, is the algebra of things, then I don't really know what the solutions look like. But I can have L is 0 or half or 1 or 3/2. This is interesting. My M values are going to behave the same way, minus L going up to L. But these half-integer values of L, they're rather strange. They're going to behave in ways that are utterly unfamiliar if what you're used to thinking about are things that actually live in ordinary three-dimensional space. But these do actually happen to have physical reality, and it has to do not so much with orbital angular momentum, the motion of a particle around in an orbit, for instance, as they do with spin angular momentum, or at least that's the name quantum mechanists, I think? I don't think I should say quantum mechanic. Quantum mechanists say is associated with these half-integer values. They have physical meaning in the context of spin angular momentum. As an example of how these angular momentum structures can be useful, consider the rigid rotator. What I mean by that is, suppose I have two masses, both equal to mass m, separated by some distance a. And I put them on a rod of length a, and I spin them around. This is a, system that can in principle be treated with quantum mechanics. The only energy associated with this system is going to come from rotational kinetic energy, since the thing is not allowed to translate. I'm fixing it to rotate about the center here. So my Hamiltonian operator is going to essentially be the rotational kinetic energy, which is going to be L squared over 2 times the moment of inertia. This is the rotational analog of p squared over 2m. I have angular momentum squared divided by twice the moment of inertia, the rotational equivalent of the mass. Now, I suppose I should either erase the hat for my Hamiltonian operator or add a hat to my angular momentum operator. I said in this lecture I wasn't going to use hats to designate operators, so I'll erase it from the Hamiltonian. At any rate, you know how L squared behaves. The moment of inertia here, I, is going to be 2, since I have two masses, times mr squared, essentially, so the mass times the radius squared, which is going to be a over 2 squared. So this is going to be ma squared over 2 for my moment of inertia. The time-independent Schrödinger equation then becomes h times my wave function is e times my wave function. That's my original. When I substitute in the specific definition of the Hamiltonian here, I have L squared, my squared angular momentum operator, divided by twice my moment of inertia, which is just ma squared. I have an over 2 here, and I have a 2 here, and they cancel each other out. If this is going to be equal to L squared acting on psi is going to be equal to E times psi, ma squared here is a constant, I can rearrange this and write L squared psi is equal to ma squared E times psi. This now, this ma squared E, this is my eigenvalue of an eigenvalue problem with L squared in it. I know what those eigenvalues are. This is h bar squared L plus 1. That's my eigenvalue, the form of my eigenvalues of the L squared operator. So what that tells me is that ma squared E is equal to h bar squared L plus 1. And I can solve this for E easily. It tells me that E is equal to, an equal sign somewhere, h bar squared L plus 1 divided by ma squared. These are the allowed energies, the energies of the stationary states, for the rigid rotator. You can just as easily go through the same sorts of arguments and write down normalized wave functions for the rigid rotator. But essentially this is a very common structure that you're going to encounter in quantum mechanics. Angular momentum is, of course, a conserved quantity in classical physics, and it's a conserved quantity in quantum mechanics as well, which means it's interesting in a lot of respects. And the quantum mechanical structures you get, either if you're looking at something like a rigid rotator now, since we could actually write a real-world wave function for this, we're stuck with just spherical harmonics for the wave functions, integer values for L, and you're going to encounter this sort of expression a lot in quantum mechanics, especially if you go on to the upper levels. Think about for a moment what we've accomplished. Solely by messing with operators and solving partial differential equations as motivated by this original hypothesis of the time-dependent Schrödinger equation, we were able to determine conserved angular momentum structures. We're even able to predict that there's going to be something strange happening for half-integer values of L in these eigenvalue equations, and that's going to be the topic of the next section in the textbook, spin. The half-integers have a lot of strange properties associated with them. So that's where we are, and that's where we're going. The machinery of quantum mechanics is obviously very productive, and we're going to keep working our way through the results of it for the next couple of lectures. How our angular momentum operators act on this general wave function. If we can express our angular momentum operators in spherical coordinates, we can write down this sort of eigenvalue equation. It will then be a partial differential equation that we can solve, in general, for any value of L or M. Unfortunately, in this lecture, we run into some thorny notational issues. I like to use hats to designate operators. Griffiths, your textbook author, likes to leave the hats off when it's not ambiguous. This is one of those cases where it is ambiguous, and I would like to use the hat form of F. When we were working with the one-dimensional quantum harmonic oscillator, we were able to derive, for instance, the ground state by knowing that the lowering operator acting on the ground state gave us 0. That was a differential equation that we could work with since we knew differential forms for the lowering operator. We can do the same thing with the angular momentum operators, but in this case, it's more worthwhile to think more generally. So suppose we just have some general psi of r, theta, and phi. This is our wave function expressed in general polar coordinates, and it would be nice to know form h bar squared L, L plus 1 was our eigenvalue. Likewise, for L sub z, we ended up with eigenvalues of the form m times some constant h bar. The L's that we got had to be half integers, either 0 or 1/2 or 1 or 3/2, etc. And the constants m that we got here had to be between minus L and L, going up in steps of 1. So our eigenvalue structure here, as I mentioned, doesn't tell us anything about the actual form. In the last lecture, we were able to, purely by examination of the structure of the angular momentum operators, derive the quantization properties of angular momentum in quantum mechanics. We were able to examine the commutators, manipulate the operators, and essentially derive the eigenvalues associated with the operators L squared and L sub z. That's nice, and it's very useful. The eigenstates associated with Hermitian operators in the Hilbert space have nice properties, but we don't actually know what those eigenstates look like. In order to get something easier to visualize, let's consider what the eigenfunctions are, trying to express the angular momentum operators as partial differential equations that we can solve with the techniques that we've been applying earlier in this chapter. The angular momentum operators that we were working with in the last lecture are expressed in Cartesian coordinates. This was very nice because the Cartesian form has this nice symmetry to it, and we could calculate commutators easily. Just by manipulating these, we were able to derive expressions like the eigenfunctions of L squared had this sort of